Hey folks, sorry I couldn't be in person today, but we're going to talk about pulleys a little today. So as you can see in the picture here, a pulley is just a disc mounted, let's say, near a wall with a string wrapped around it, and you can have a mass on either end of that string. This particular way that we can use a pulley to make it easier to lift and lower objects is called an Atwood machine. If you see a different setup, it wouldn't be called an Atwood machine, but that's what this is called. And the pulleys we're going to deal with at this point in the course are all massless, frictionless pulleys. The pulleys themselves are not bulky, they have no inertia, and they rotate on an axle without any friction. What that does is it ensures that the tension force on each side of the pulley is the same. So we're continuing with this theme of when you have a rope, the tension force in both ends of the rope match each other. All right, so what do we want to do here? Well, one thing we can do is we can ask, what is the tension in that rope, and what is the acceleration of this system, of this two-mass system? Either the system doesn't accelerate or it does, and if it does, one block will rise and the other will fall with an increasingly great speed. So let's draw free body diagrams for both these objects. We have a tension force Ft pulling mass 1 up. We have a gravitational force Fg1 pulling mass 1 down, which is equal to mass 1 times little g. On the other side, we have an equal tension force, as we just mentioned, pulling mass 2 up. And we have a gravitational force Fg2 equal to m2 times g, pulling mass 2 down. All right, now the best way to find the acceleration of this system is to group the two masses together. Group the masses together as a single system. Why is this a nice thing to do? Well, for one thing, when I group the two masses together as a single system, I'm acknowledging the fact that they will have the same acceleration. The rate at which one mass accelerates must be the same as the rate at which the other mass accelerates, or else the string would break, and we're imagining that doesn't happen. So the blocks have to speed up and slow down around the pulley as a unit together. Also, grouping them as a system means I don't really have to worry about those tension forces just yet, because the tension forces are inside the system. It's the force that one block exerts on the other block through the rope. So there are really only two forces on the two-block system. The force of gravity on object 1, which tries to pull the system clockwise, and the force of gravity on block 2, which tries to pull the system counterclockwise. In terms of what direction is positive and what direction is negative, what I'm going to do here is going to seem a little suspicious, but it's totally fine. I'm going to say that the clockwise direction is my positive x direction. So up on the left, left to right on top, and down on the right. This clockwise orientation I'm going to define as the positive direction, and a counterclockwise orientation for anything, a force, an acceleration value. A counterclockwise orientation would be negative. Okay, so let's apply Newton's second law to the system. The net force on the system in the x direction is mass times acceleration. Now, in the positive x direction, clockwise direction, we have the force of gravity on mass 1. That's trying to pull the system clockwise. And in the negative direction, the counterclockwise direction, we have this force, the force of the Earth pulling gravitationally on mass 2. And one of those forces is clockwise, positive. The other is counterclockwise, negative. That's why I have that negative sign. Those two gravitational forces are competing to make the system accelerate in one direction or the other. And that equals the total mass of the system times the acceleration of the system. All right, so if I wanted to solve for the acceleration of the system, I could just divide each side of the equation by the sum of the masses, which is in parentheses right now on the right-hand side. And then a nice thing to do is to factor out little g from the numerator. Factor out little g from the numerator, and we get this result. So we're going to kind of test this out and see if this result makes sense for some special values of m1 and m2. But just notice the acceleration of the system is just the free fall acceleration due to gravity times this thing, this combination of masses. So the mass values definitely determine what the acceleration will be, but also the free fall acceleration value on whatever planet you're on helps determine the acceleration. Okay, so that's the acceleration of the system. Now I want to find the tension. I want to find the tension in the rope. So let me get rid of the grouping now. I no longer want to group these objects together as a single system, because if I do that, the tension in the rope is inside the system and it doesn't make an appearance. I want to look at the objects separately now. We can look at object 1, for instance, mass 1, which is on the right-hand side of the screen. And let's apply Newton's second law just to mass 1. This is how we can come up with an expression for the tension. So mass 1, gravity is pulling mass 1 down. And for mass 1, that is the positive direction side of the pulley. So m1g is the gravitational force pulling mass 1 in the positive x direction. The tension force pulls mass 1 up, which is opposite the positive x direction. So that's a negative force, and that equals m1a. We can substitute in the value of the acceleration that we just obtained up here. The acceleration of mass 1 is the same as the acceleration of mass 2, because they're connected by a rope. And this looks pretty ugly right now, but if you have the inclination, you can solve for tension. You can solve for the tension in the rope, and you will get the following result. 2m1 m2 over m1 plus m2. Now, it takes some algebraic manipulation, finding common denominators, distributing and stuff like this, but the result is pretty compact. So this is our tension force, and from above, we have our acceleration value. I will not ask you to algebraically solve for the tension force on a test, but I will ask you to apply Newton's second law to find the acceleration. So this is not a result that you memorizing is not going to do it. You have to be able to draw the free body diagram, apply Newton's second law, and know how to do this. The resolution of my stylus here is not great, but know how to do that. All right, let's play around with the results a little bit and see what the results are telling us about certain special cases. I'm going to erase all this. And we really just need the answers. So we have the acceleration over there, and we have the tension force. Both the acceleration and the tension depend on the particular mass values, and they also depend on the free fall acceleration value. And I just realized I forgot something here. Made a mistake. Let me add it in. The tension force has a form that is this times little g. Obviously, the tension force can't have units of mass by itself, but mass times little g gives you units of newtons. All right, let's make a little chart for ourselves. And in this chart, we're going to have acceleration in the x direction, the force of tension, and particular conditions on the mass values. For example, we can look at mass 1 equaling mass 2. We can look at, let's say, mass 1 being bigger than mass 2, or mass 2 being bigger than mass 1. And we could also look at, let's say, mass 1 being much bigger than mass 2. We'll see what that's all about in a moment. All right, well, if the mass values are equal, we can figure out what the acceleration is. Take a look at the acceleration expression. If the masses are equal, then the numerator is 0, and the denominator is not 0. But that means the acceleration is 0. So the acceleration is 0 if the masses have the same value. Maybe both masses, m1 and m2, just equal little m without a subscript. So little m minus little m is 0, and there is no acceleration. In the tension expression, if little m1 and little m2 both just equal little m, you can make that substitution and see that the tension is just mg. Because the numerator would be 2m squared, the denominator would be 2m. That means the expression in parentheses is just m. All right, let's think about that for a second. If the masses are equal, there's no acceleration. This has to be the case. There's total symmetry if the masses are equal. One mass is not going to rush down while the other rushes up and picks up speed because the masses weigh the same. So if the masses are equal, I can imagine three things. I can imagine everything just sits there at rest and there's no acceleration. Or I can imagine, well, these things are already moving and they'll just continue to move with one dropping and one rising at a constant velocity. And thirdly, that can be happening in the other direction. Remember, not accelerating means remaining at rest or maintaining a non-zero constant velocity. And how about the tension expression? Can we make sense of that? If the system doesn't accelerate, each individual block doesn't accelerate. If each individual block doesn't accelerate, the tension force pulling a block up must be just as strong as the gravitational force pulling a block down. So the tension of the rope equals the weight of either block, and the weight of the two blocks are the same, mg, if the masses are the same. All right, what if m1 is greater than m2? There's not much to say here. If m1 is greater than m2, the acceleration numerator is positive. So all I really know here is that the acceleration in the x direction is positive. And if m1 is bigger than m2, it's not that interesting what's going on with the tension. But m1 being bigger than m2, if the mass on the right, m1, is bigger than the mass on the left, m2, the acceleration will be in the positive x direction. So either the system rotates clockwise, faster and faster, or if the system is already rotating counterclockwise, it will slow down because it'll be accelerating in the other orientation. All right. What if m2 is bigger than m1? If m2 is bigger than m1, the numerator is negative. Again, take my word, there's nothing interesting to say about the tension value, but m2 being bigger than m1 means the system is accelerating in the negative direction, counterclockwise. Either both blocks are speeding up together counterclockwise, or both blocks are moving clockwise but slowing down because the acceleration is counterclockwise. Right, let's look at the last condition, which I think is really interesting. What if m1 is huge compared to m2? The way I like to think about, well, before I tell you how I like to think about it, let's just see what the equations tell us. So if M1 is huge compared to M2, maybe M1 is like Elon Musk money, and M2 is like Mr. Frankel money. You take Elon Musk money and you subtract Mr. Frankel money, because M1 is much, much bigger than M2, it's basically just equal to M1. Subtracting my money from Elon's, Elon still has the same amount. Similarly, if I have Elon Musk money in the denominator and I add Frankel money, I'm adding dust, literally, compared to what he has. So basically, I can ignore M2 when I add it or subtract it to or from M1, when M1 is huge compared to M2. Hence, I basically have in the parentheses, ignoring the minuscule M2 value, I basically have M1 over M1, which is just the number 1 times G. So if M1 is huge compared to M2, the acceleration is approximately equal to G. Let's try to make sense of that. M1 is like an elephant over here, some huge object, and M2 is like a tiny little piece of dust. In that situation, it doesn't even matter that there's an M2 there. The elephant is basically just going to free fall. So the system is going to accelerate at free fall acceleration because there's basically nothing of significance on the lighter side of the rope. Now, the equations are telling me that, and putting it into words like this hopefully makes sense for you of the equations. If one mass is titanic compared to the other, the titanic mass just free falls, essentially. All right, what about the tension force? Well, if M1 is huge compared to M2, again, we can ignore adding M2 to M1. And what this becomes is 2M1 M2 over M1 times G. I can ignore the little mass 2 whenever I add it to M1 or subtract it from M1. When I multiply them, I have to treat them equally. A big number times a little number is not just simply a big number where you could ignore the little one. But now M1 cancels out, and I get 2M2G. So the tension in the rope is 2M2G. Now this is interesting. The tension in the rope has nothing to do with the big mass, M1. It only has to do with the little mass, M2. Let's talk about why this is the case. So I have my M2, and I've got my huge M1. Now, one thing to note is that the weight of the little guy is really tiny compared to the weight of the big guy. The tension force in the rope is 2M2G. 2M2G. Now, I didn't really draw these to scale because if I did, M2G would be really, really, really huge, like 100 times bigger than M1G. But let's think about it. The tension in the rope is twice the weight of mass 2. Well, that kind of helps me understand why M1 just free falls. It doesn't quite free fall, but close. Because there's this huge gravitational force pulling it down, like the weight of an elephant. And there's the weight of 2 bunny rabbits pulling it up. Well, 2 bunny rabbits versus an elephant, the elephant's basically just going to free fall. So that explains why object 1 accelerates down at roughly 9.8 meters per second squared. Now let's look at object 2, okay? Object 2 has a force equal to twice its weight in tension, pulling it up. So the net force on object 2 is, let's see, we have m2g down and 2m2g up. So the net force on object 2 is just m2g pointing up. That means object 2 has a net force equal to its weight pulling it up. But I know what happens if the net force on an object equals an object's weight. The object's acceleration is 9.8 meters per second squared. That explains why object 2 is accelerating up at 9.8 meters per second squared, because the net force on it is m2g in the upward direction. And we have to be a little careful here. From the elephant's point of view, it's basically free falling. The elephant can't even feel the tension in the rope, the tension equal to the weight of 2 bunny rabbits. The bunny over here is accelerating up at 9.8 meters per second squared, but that does not feel like free falling. The tension force on the bunny's ankle, let's say, is not insignificant compared to the bunny's weight. It's actually twice the bunny's weight. Imagine suspending a bunny from a rope tied to the ceiling and it's hanging by its ankle. Cruel and unusual punishment, okay? But that's going to hurt the bunny's ankle eventually because there's a tension force pulling on the bunny's ankle equal to its own weight. But the tension force on this bunny rabbit is twice the bunny rabbit's weight. The bunny's going to feel a very strong upward pull from that rope. It's not going to feel like free fall at all. There's going to be this huge tension force on the bunny's rope. However, that tension force will make the bunny accelerate up at 9.8 meters per second squared. So it moves along with the elephant, which is effectively free falling at 9.8 meters per second squared. All right, this is a good example of how obtaining equations and then seeing the results that those equations give for certain relationships with the variables lets you kind of understand what the equations are telling you a little more clearly. To recap, group the masses together to find the acceleration, and then look at one mass individually to try to find the tension force. Okay, let's look at another situation. Sometimes this is called a modified Atwood machine. It's something that you'll encounter in problems. So I have a table and I have a pulley at the edge of the table. That pulley is like fixed to the table here. And then there's a rope and I have a mass M1 and I have a mass M2. And let's say there's no friction for now. No friction. Okay, the free body diagram looks like this. There's a force M1G pulling mass 1 down. There's a tension force Ft pulling mass 1 up. There's a tension force Ft pulling mass 2 to the right. Of course, there's a gravitational force pulling mass 2 down and a normal force pulling mass 2 up. And there's no friction. So that's it. 3 forces on mass 2, 2 forces on mass 1. And like before, I'm going to have my x-axis wrap around the pulley clockwise. So clockwise is the positive orientation. Let's answer the same 2 questions. What's the acceleration of the system and what's the tension in the rope? So let's group the objects together again, apply Newton's second law to the system. When I group these objects together, I notice the following. First of all, the normal force cancels with the gravitational force on object 2. So those forces cancel out. Secondly, again, the tension, just like before, the tension forces are inside my system. They cannot affect the total behavior of the system, therefore. The only external force on the system is the force of the Earth pulling down on mass 1. All the other forces either cancel or they're inside my system. Therefore, the net force on the system is just the gravitational force on block 1. And if I divide each side of this equation by the sum of the masses, I find that the acceleration of the system is m1 divided by m1 plus m2 times little g. Okay. How about the tension force? Let's apply Newton's second law to mass 2. The net force in the x direction on mass 2 is mass 2 times its acceleration. But the net force on mass 2, if I focus in just on mass 2, the normal force and the gravitational force cancel. So all we have is the tension force pulling mass 2 in the positive direction. So the tension force is the only force pulling mass 2 in the positive x direction. That equals mass 2 times the acceleration. And the acceleration is m1 over m1 plus m2 times little g, which is what we solved for up here. Therefore, the tension in the rope is m1 times m2 over m1 plus m2 times g. Very similar to the tension in the previous problem, except there's no 2 in the numerator now. So again, let's try to make sense of these results. We have acceleration in the x direction. We have a formula for the tension in the rope. And then we have different conditions. In this situation, in this situation, the masses being equal is not that interesting. Just notice, this system will accelerate in the positive x direction. There's no friction. If M1 were a bunny rabbit and M2 were an elephant, the thing would still slowly slide to the right, slide clockwise, because the system is being pulled in the x direction by the Earth's gravity on the hanging mass, and there's no other force in the negative x direction on the system. So let's look at the following conditions. M1 is huge compared to M2, much, much bigger than M2. And M2 is huge, much, much bigger than M1. All right, so let's look at the first condition. M1 is huge. So if M1 is huge compared to M2, then I could ignore adding M2 to M1 in the denominator of the acceleration expression. I then have M1 over M1, which is the number 1, times little g. So if M1 is huge compared to M2, the acceleration is approximately equal to little g. Sorry. How about the tension force? If M1 is huge compared to M2, I don't have to worry about adding M2 to M1. I'm left with M1 times M2 over M1. So the M1 goes away, and the tension force is just equal to M2 times G. Now, understanding these results is the same as understanding the previous result, where you had an elephant on one end of the pulley and a bunny rabbit on the other end of the pulley. If M1 is huge compared to M2, then I could basically ignore that M2 is even there. M1 is basically an elephant with a string tied to its ankle, and there's nothing on the other end of that string. Therefore, the elephant will just free fall. And that, I'm sorry, I'm struggling to get my top to work here. I'm trying to select there we go. Okay, so if you have an elephant and a bunny rabbit, the elephant doesn't even sense the bunny rabbit is there, and the elephant free falls. So both the elephant and the bunny rabbit will have an acceleration of roughly 9.8 meters per second squared, hence the result over here. And the net force on the bunny rabbit is just the tension force to the right. That has to equal Well, the bunny rabbit's mass times its acceleration, which we just said is going to be equivalent to free fall acceleration. So the tension in the rope has to be m2g. That tension of m2g doesn't prevent the hanging elephant from basically free falling, but it does make the bunny rabbit accelerate at 9.8 meters per second squared. What if m2 is huge compared to m1? What does that look like? If m2 is huge compared to m1, then the bunny rabbit is hanging over the edge and the elephant is on the table. Pardon me here, having Zoom issues. Okay, so M2 is the big one. So we have an elephant up here and a bunny rabbit down hanging off the table. Well, let's see what the expressions tell us. If M2 is huge, I could ignore M1 when I add M1 to M2. And the ratio M1 over M2, which I'm left with in the parentheses here, is a super, super tiny ratio because M2 is huge. So the whole thing, the acceleration is roughly 0. Basically, nothing happens if you have a tiny thing hanging over and a huge mass on top. It won't be exactly 0. It will be like bigger than or roughly equal to 0. There will be some small acceleration. How about the tension? If M2 is huge, I could ignore M1. Then I could divide out by M2, and I get 1 G. Something is wrong here. What is wrong here? Something strikes me as odd. All right, nothing strange. So M2 is huge compared to M1. Basically, there's no acceleration, and that means mass 1 is just hanging there. If mass 1 is just hanging there, the tension on it must pretty much be equal to its weight, must approximately be equal to its weight. So I'm picturing a static system. This huge mass is on the table. This tiny little mass is dangling over. Basically, nothing's accelerating. And the tension force in the rope is basically matching the weight of the little thing, M1, that's hanging over the edge. These formulas we derived, though, apply for any combination of masses. So even if one mass isn't huge compared to the other, you can use these formulas to figure out what the precise acceleration and tension values will be. All right, I don't want to hit you with too much information in this video format, but just to draw some things to your attention so you anticipate some things. You could also have a pulley mounted on top of an inclined plane where you have masses like this. There'll be a homework problem or two that deals with this setup, but let me just literally put into words what to do in all these situations. So the first step is always group objects together as a system to find acceleration. Oh, actually, before you even do that, there's step 0. Step 0, which is draw a free body diagram. Then group the objects together to find the acceleration. And then you can apply Newton's second law to individual objects to find the tension force in the rope that's present. Okay, so sorry I couldn't be in person today, but there are some multiple choice and some free response questions on AP Classroom. Work to get together on these, do the best you can, put in a full effort, and there'll be ample time to ask me questions about the problems, which I anticipate you'll have when I return later this week. All right, have a great one now.